All right. So thank you very much. Thank you very much for being here today. Also those beyond the screens connecting online. Thank you, Isabel, for joining us today. It's our pleasure to have you here. Isabel is a full professor at the School of Aerospace Engineering at the Polytechnic School of Madrid. She was a teacher of some of us quite a while ago. So it's a pleasure to have you here talking about your more than 25 years of research experience in the field of thermal control design of different scientific instruments. She has been contributing to NOMAD instrument for the ESA ExoMars mission, also at the MEDA instruments for the NASA Mars 2020 mission, Perseverance rover, and also at the Sunrise 1, 2, and 3, and the FEE instruments for the ESA Solar Orbiter. So that's quite awesome, and I think it's going to be very interesting to listen to what you have to tell us today. On top of that, she's the coordinator of the area of space at the Spanish Agency of Research that belongs to the Ministry of Science and Innovation. And she's going to be talking today about thermal control of space systems. So thank you very much again, Isabel, for being here.
Thank you.
And the floor is yours, please.
Thank you very much. So thank you, all of you, for giving me this opportunity. It's a pleasure to be here. It's only 30 minutes, so what I'm going to present is just some highlights of what we usually do in the field of space systems thermal control. I have to say that, in fact, I think most of you will have studied, maybe in some subjects, spacecraft thermal control, so the first slides will be very basic for you. But what I wanted to point out is mainly the research opportunities we have and what we do, let's say, to do research within this field that is in fact an engineering field. So we have to go beyond the merely engineering tasks and try to find opportunities for research. And what I'm going to show you here is just some highlights about what we do, taking as baseline these engineering activities we do in the framework of space missions. Mainly, as Manuel has said, some of them we have participated with different levels of responsibility in different missions. Maybe the last one with the most complete is Solar Orbiter. We had the responsibility of the thermal control of one of the instruments from the very early stages, from the beginning of the mission concept up to now it's in orbit, so it's on operation. So we are now analyzing flight data. So to do this, maybe for this is very basic for you, but I don't know to what extent all your background is aerospace or not. So very, just some spots of why we need in a space system a thermal control subsystem. So at the same level, when you study space thermal engineering, thermal is at the same level as the other subsystems like structural or propulsion. So you have there, it's very important, and the main reason is that all equipment, all device you can imagine can work properly within a temperature range, and it doesn't work properly out that temperature range, and it may even break down. So we also have requirements in terms of gradients. We work mainly in space missions, and in space missions, the payload, that is what we call the science instrument, is mainly composed of optomechanical devices. And optomechanical devices are very sensitive to temperature and to temperature gradient. So thermal, one of the aims of the thermal control is also to keep the gradients under control. And also temperature stability. This is related with the measurement, with the frequency, with the stability we need for some devices to measure properly. And we have to do, this is the same on Earth systems. And what's the main difference? The main difference between Earth systems and space systems is that we have to get this with in a very hostile environment that is mainly characterized by the vacuum environment. We don't have the air. We have here that we are all experts in fluid mechanics, and we know how to use environmental air to cool down systems. We have a cold sink that can be very useful. That is, well, it's more or less 3, 4 Kelvin, 2 Kelvin. It depends on where you define it. And we also have extreme environmental conditions that are also changing very quickly. And this is not good because we are, let's say, our systems are subject to either very hot or very cold conditions. So we have to design our instruments to be able to cope with those extreme conditions. So I'm not going to go through this whole slide. I will leave it here. This is what the standards, the ECSS, when we work in space missions, tells about the standards. The standards tell about the aim of a thermal control subsystem. The first one is to maintain all the components on board a spacecraft within the allowable temperature range. And we have to do it along each mission phase. So we cannot forget, sometimes we try to, or we think in the nominal phase of a mission, but sometimes the sizing phase of the thermal hardware of a mission is not just the operation phase. But we have, for instance, I can tell you about Solar Orbiter. That is one of the most recent ones. Solar Orbiter is going to be very close, is going to approach very close to the sun. So we think that is a very hot environment. In principle, yes. But it has, the mission, the spacecraft has a huge heat shield, and some instruments are hidden behind the heat shield. So the environment is not going to be so hot. However, Solar Orbiter has several flybys with Venus, and in that case, the spacecraft is not guaranteeing the pointing. So instruments that are designed, in fact, to operate shaded from the sun, in that case, they can have both albedo from Venus or direct sun on that. So we have to think not only on the nominal phases, but also transient phases until we reach the nominal operation. We have to do this for all conditions, not only operational, also non-operational. We have to guarantee the optical performance. We have to avoid damage. As I said before, temperature stability, to guarantee that we don't surpass the temperature, we don't, let's say, exceed the temperature gradients based on the limits. We have also to guarantee that the interfaces requirements are met. This happens when, for instance, you design an instrument, you have interface requirements in terms mainly of the heat flux you can put, for instance, through a surface. So systems are not flying, they are bolted to a surface, and the amount of heat you can dump into the platform may differ in each mission. Sometimes you have to insulate it, sometimes you have to use just the platform to get rid of the heat we generate inside. And one of the important points is that we have to identify, I don't know if I have a pointer here. We have to identify the relevant parameters, and to be able to, if we want a robust design, we have to know what are really the parameters that have more influence on the thermal behavior of the system. And we have to try to manage them in a way that they are, let's say, the robustness of the design goes with the, let's say, the capability of the system to react to changes in these parameters. Okay, I'm speaking maybe too fast. Now, so just some spots. The main parameters we have. How we do this? So the main parameters that drive the thermal control subsystems are, of course, the spacecraft environment. Solar Orbiter has nothing to do with a mission to Jupiter, or as you can imagine, or a rover on the Mars surface, or it depends, of course, on the mission. Maybe in other type of missions, like commercial missions, or maybe navigation or geostationary orbits, the environment is more similar to all spacecraft of the same type. But in the case of science missions, each mission is different. And that's a problem because it's difficult to let's say, recycle ideas or to have kind of recurrence design. Also, the heat dissipated on board the spacecraft. Of course, the thermal design of a geostationary telecommunication satellite dissipating a lot of power has nothing to do with a science mission. So the amount of power dissipated is one order of magnitude of difference between both. how this heat is distributed, of course, the thermal requirements. So it has nothing to do to have an equipment that say, hey, this can live between -20 and 40, or this can live, this has to work at, I don't know, 10 Kelvin, for instance, no? Some detectors, or even sub-Kelvin, we are in that range. And the configuration of the spacecraft and the pointing of the spacecraft, so everything is related to that. And what we do, how we work on this, up to now we are talking of engineering problem, so we are part of design teams, and what we do in space, and I don't know to what extent you are involved in space missions, is that it's very difficult to innovate in space. So you have to prove that what you are doing has been used previously. Otherwise, you have to prove it's going to work, and it's much more complicated. So the first thing is that you base your design on previous experience. You start, and for me this is very, very important, with basic semi-analytic calculations. I think this is being lost right now. So I find now very few people with capabilities of doing hand calculations with just writing the equations and giving results roughly. At the very early stages of a mission design, this is very important. Once you have a concept, then you start with more complex simulations, using now tools to do that. In our case, we use mainly Satan. Satan TMS is one of the tools used in the European Space Agency. We run steady cases, transient cases. We do laboratory tests, and either in engineering models or on the whole system. And we have a lot of limitations. We have to be aware that our calculations and our results have a lot of uncertainties. So one of the things we will have to work on is the uncertainty calculations or the error propagation from the input data we have up to the results we get. We have to know that we have to rely on testing. It's very difficult to predict or to give values to some of the inputs, some properties. We have to measure them. There's no other way to determine them. And we also have to know that this design task is part of an engineering, systems engineering task, and we have to iterate with all the subsystems, all the subsystem of a spacecraft. Okay. Now, this is a bit where I'm going to step. What are our tasks? These are mainly engineering tasks, and what I'm going to do now is to review them, to explain the process, and to say how we do, what we try to do, because I have also students, I have PhD students, I have to give them the possibility of, within this framework, to do their PhD thesis, to work on this. And it's very difficult. I think you will be aware of that in a technical field, to publish papers and so on. So we have to do something to go beyond the merely engineering problem and to try to find topics where we can publish something. So, and this is what I'm going to try to do. So this is the process, and afterwards I'm going to put some, let's say, like side activities, but related to this. So our main tasks, what we do first, we have to set up thermal models of the system. It's in the end, if we want to check that we are fulfilling all the requirements, that we are, let's say, achieving the objectives, we have to calculate temperatures and heat fluxes. That's mainly what we will have to do. So we have to set up a thermal model of the system. To run this thermal model, and this is very important, you have to define what we call the sizing cases. Sizing cases in thermal control are, well, the dimensioning cases, we also call it that way, is what we are going to use to select the thermal hardware. So mainly, we will have to select thermo-optical properties of the system, of the alpha epsilon, so solar absorptance, infrared emissivity, thermal finishes of the surfaces. We will have to size radiators. We will have to size heaters. Sometimes a bit more, but those are the three basic things, and some thermal connectors, heat pipes, to do that. So to do that, what we usually do is to define what we call the hottest case. So we identify the hottest scenario, and with the hottest scenario, what we do is to size the radiators. And once we have the radiators, we go to the coldest scenario, and in the coldest scenario, what we do is to size the heaters we need, because with those radiators, maybe we will have subcooling in the coldest scenario. And that's the typical engineering approach. So we are going to extreme conditions, but that means that we are, on one side, we are oversizing the system because we were there with our margins. But on the other hand, for scientists, and we work for scientists, they want to know really the performance of their instruments. And to do that, they want to know what's the temperature they are going to encounter in orbit. It's not only to design, and just I say, hey, yeah, your instrument is going to be between this and this. But scientists don't want that. They want to say, hey, don't tell me that. Tell me at what temperature my instrument is going to work. And that's a different thing. That's what we call the performance cases. So we have to be able to identify the performance cases and to be able to predict with certain accuracy what this case. Okay, once we have done this, we calculate temperature and heat fluxes, and well, this is a loop, in fact, and we size the system, surface finish, radiators, insulation materials, whatever we need to do that. We have to calculate, this is very important, the contribution to the both mass and power budget of the system. So we need, as you know, both power and mass. In fact, it's mass, because power, you can get power with mass, is the most appreciated value in a spacecraft. That is what really is limiting everything. So we have to calculate this, and we give this to the systems engineering. And in addition to that, you may think, hey, we already have a design, but it's normal, and it's a common practice that during the design of an instrument, we have to, let's say, put our model in a higher hierarchy model. And that means that we have to reduce our model so that, let's say, the main contractor of the spacecraft, it's usually one of the big companies, Airbus, in Europe, at least Airbus or Thales, they are going to use our model to put it within the spacecraft model to predict the whole behavior of the system. To do that, what we have is to create in thermal control, we call it a reduced thermal model. In other areas, you can read about surrogate models, or they use a different name, but in fact it's the same. We have to provide a model that behaves in the same way. And the problem with this is that it's not so easy, because these reduced thermal models have to behave in the same way in any case, in any scenario. So we are, let's say, sizing for two extreme scenarios. We are predicting for the performance scenarios, but we have to, let's say, reduce the model and guarantee that this model behaves like the detailed thermal model in all possible scenarios. So that's we have to together with the model, we have to deliver what we call the correlation. So that is the proof that our reduced model works in the same way as the detailed thermal model. In addition to that, the validation of thermal, not only thermal, of design in space is generally done not only through analysis, like in this case, but also with testing. So the thermal engineer also has to let's say, to cooperate or to contribute to the test definition, test procedure, test results analysis. And finally, we need here another correlation, because we have to correlate test results to model. So this means that we will have to update our model with the test results. And fortunately, if you are lucky, the changes are not too severe. You don't have to do any more, but if you find here that your predictions were not good, sometimes you even have to change the hardware you have defined. So that's why tests in between, when you really don't know the properties, are very interesting. So this is here, data models and even the design. So as you can see, this list, this is what we do. Later maybe, because I'm running out of time, we can tell you how we work in the environment, how we enter this consortia and of science and scientists and technicians and to do this. But if you read this list, this is, let's say, engineering, thermal engineering of spacecraft, and we have to find the opportunities to enter here and to do some research here or some activities. That's what Manuel told me to talk about the opportunities, and this is what I'm going to do. First, one comment. Thermal models, these are some screenshots of Satan, are very rough, very ugly. Okay, maybe if you are used to mechanical, to structural models with, let's say, very small elements, you see this, and you see this, and this is maybe 3 meters or something like that. You see the size of the elements, and this is ugly. So the geometries are ugly. The capability of reproducing the geometry is like rough, and that's why we have to be able to manage this from outside to have the right results. For us, this is more than enough. Okay, if I have an isothermal surface, I don't need more nodes. I don't need more elements. Okay, so for thermal engineers, it's very clear. I can tell you kind of anecdote. I was maybe 20 years ago. I had a model of, it was this, a preliminary version of this. I had a model with about 700 nodes, more or less. And a student came to work with me. I told him, hey, you have to update this model. But there are very few nodes. I cannot do that. And they say, do whatever you want. And he built a model with 7,000. So he multiplied by 10 the model I had. And when he ran the results and he ran the model and he got the results, I asked him, what are the results? It's the same as with your model. So if you identify that your surfaces are going to be isothermal, you don't need more nodes. You don't need, and mainly because here we have radiation calculation and they are very heavy and very time consuming. Now we are improving a lot with the new capabilities of computing, but I'm talking maybe 20 years ago that was running this model, maybe it could be 1 day or 2. So now I come back to the list, and now I'm going to put some bullets inside the list telling you what we do. And as I said, these are not really necessary activities, but like side activities we try to find. Whenever we find a problem, we scratch and say, hey, here there is a problem. Let's see if we can go further, even if it's, let's say, beyond the scope of the project. Okay, so in this case, for instance, I give you here the reference in case you have interest. Related to setup of the thermal model, calculation of accurate linear conductors. With the image you had before, the geometries are very simplified, but sometimes we have complex geometries. For instance, if we have a bracket to hold a mirror in a optomechanical system, with this type of geometries, you can imagine that we cannot have a very accurate geometry. And when you have a bracket, the thermal modeling of the bracket is very important because the heat received by wherever the bracket is holding, that heat is going to be transferred to the platform through the bracket. So it's important to have a good and accurate, let's say, modeling of the bracket. So one of the things we did was, let's say, to devise a new method to calculate linear conductances of more accurately than the program, than the tool we have, and very efficient from a computing point of view. We have, and again, we used this kind of surrogate model. So we had a very, very, very accurate, here, you cannot see it here, but we had in this case this platform, and here, this may have, I don't know, but maybe 1 million nodes, very, very accurate. We computed this, and then we go to our model with this. So we do it the other way around. Our detailed model is like the reduced model for an extra detailed model. And we created an algorithm. Whoop, it didn't work before, and now it will work. Okay, we created an algorithm, and okay, if you are interested, it's here. More things. In this case, another point where we scratch a bit and we went beyond. We were working with rarefied atmospheres. We have found rarefied atmospheres both in Mars and also in Sunrise. Sunrise is a balloon-borne telescope. Now, in 2 weeks, we are going to launch, in 3 weeks, we're going to launch the third, Sunrise. And in rarefied atmospheres, sometimes heat transfer may be negligible from the thermal point of view in terms that it's not really going to affect too much to the temperature of the systems. So you even can discard it in the thermal calculations, let's say in a macroscopic, from a macroscopic point of view. However, if what you want to measure is the ambient temperature, you need that system that has to be in equilibrium, thermal equilibrium with the atmosphere, and that's where you have a problem. So the instrument made on board the Perseverance, the Mars 2020 Perseverance rover, has a system of thermocouples that are like a kind of joke with some wires there. And the thermocouple is in the center of that wires. That's where the welded union is. If you would really want to use the thermocouple to measure the air temperature, you have to guarantee that that wire is in equilibrium with the ambient. And that wasn't clear. In that case, we entered later, not at the very beginning of the design. We just have to analyze what was happening there. And we realized that when we started to model the convection with ambient air in Mars, when you had a very, very tiny, thin wire in a very rarefied atmosphere, we were very close to the limit of the continuum. And we analyzed, because we received some correlations from NASA to do the thermal convection correlations for wires, and okay, the Grasov was there more or less in the order, but when we tried to go beyond, we realized that we were very close to the Knudsen number, and we were already in the transient phase. So what we did in this case was to measure it. We didn't have to do it for the project, but we discovered that nobody had done it before. So we set up a thermal experiment, and we measured convection there. More things. In this case, balloons and the thermal environment. Balloons are more and more used every time. So ballooning, I'm talking of stratospheric ballooning. It's a way to access space or to look at space from outside 99% of the atmosphere. That is what the scientists don't want. They don't want to see through the atmosphere that because of the different factors, either they don't access the UV band or because they have turbulence. But at 35, 36 kilometers, it's fine for them. So ballooning is now a platform used more and more often for astronomy. So what's the problem with that? That in the case of Sunrise, for instance, they launch Sunrise from Kiruna, in the north of Sweden. The winds in summer are very predictable, and they follow parallel, so they are going to circumnavigate the pole. Because of and now more obvious political reasons, they cannot done the complete circle because they would have to overfly Russia, and it's completely forbidden because the balloon it's launched from Kiruna, but it's operated by NASA. It's a NASA balloon. It's obviously not only now, but the first Sunrise was launched in 2009, and it was already forbidden. So they released the payload. It's in northern Canada, and in June now in this season, they have 24 hours of sunlight, and it's a very good platform for solar observation. What happens there with the thermal? I'm coming back to thermal. Thermal, the problem with these balloons is not really the steady state up at 35, 36 kilometers. It's what happens when during the ascent phase. They have to pass through very cold winds and so on. And in fact, the sizing case is just the ascent. So in this case, what we did is to analyze the ascent and also to use statistical data from different sources, NOAA, CERES, to better understand what's the behavior there and to have a more realistic prediction. Another topic, completely different, uncertainty calculations. And I said before, we have to determine temperatures and heat fluxes, and we have to give the results, and it said, no, the temperature of this is 20 degrees. No, it's 20 degrees plus, minus, wherever. So to do that, we need to calculate, it's like an error propagation, and this is a nonlinear problem, very heavy of calculations because we have all the radiation, the radiation exchange between all surfaces, and it's, the methodologies are not very, let's say, straightforward and not very efficient. So what we did in this case is to define a new algorithm to like generalize one existing method, and it proved to be very, very efficient. Now, this was just a case, and now we are trying to expand this and to go beyond and to do more about this. More things. Correlation. As I said before, we have to continuously correlate models. We have to correlate both between detailed and reduce models, and also to have to correlate between models and tests. In fact, the problem is the same in both cases. So we have to compare two models, and we have to, let's say, we have a model that has to give the same results as either a test or a very detailed model. The problem here is that the methods that we find sometimes first, we have to correlate, taking into account different load cases. So it's not only one case, but as I said before, we have to do it, let's say, in all possible cases, the sizing cases, performance cases, and we have to do this with an algorithm, with an efficient algorithm. And this is what we did in this work. More things. I'm going beyond the 30 minutes, but up. This one. What? No, maybe because I don't know if it's just some highlights about what you want to do. And this one related to model reduction. Okay. One of the tasks is to reduce the model. It's like to generate, what I said in other fields, what we call surrogates models that we are going to put in a higher hierarchy model. And the way a thermal model is done is through, in fact, we have like two models. One is what we call the geometrical mathematical model, and it's a model that represents the geometry, and we are going to use that to compute external loads, so solar, albedo, infrared, radiation from planets, and also to calculate the radiation exchange factors. So we need the model has to be representative of the geometry of the system. And on the other hand, we have what we call the thermal mathematical model. That is the set of differential equations we are going to solve to solve the heat transfer, the energy equations. So the problem, maybe I can go here now, is that if we have, for instance, this model, and we want to, in this case we did it, here, this one, I think it has like about 3,000 nodes, that model. And we had to reduce this to 40 nodes. So, and we have to give 40 nodes, but with the same geometry. The envelope has to be the same. And when they put this into a higher hierarchy and it starts to compute radiation exchange of the elements inside and with the elements outside, the results have to be the same. So the way used to do that is completely manual. So a thermal engineer sits in front of the computer. The normal thing is that they start with a box there, and they start to touch with the coefficients until you have the same result. So what we tried was to, let's say, automatize this in a way with some criteria, because for me it's not, let's say, we should improve the way that the result, the reduced model shouldn't depend on the person you have sitting in front of the computer. So it should be something that should be optimal or quasi-optimal, and not depending on if it's you or it's me or it's my colleague who does it. And in fact, it is the way we done it. And to do it, we have to do it in an mathematical way. And this is what we did here. It's a quasi-autonomous thermal model reduction. And the problem with this is to keep the physical meaning in these reduced models. We have to keep the physical meaning, we have to keep the geometry, and it's not so obvious to do that. And I think that's all I want to show you, that just to tell you that science missions in space are usually very, in this case, very challenging, mainly even thermally, sometimes thermally. So, and I love it, I like it, and for me it's very challenging when you have a mission. It has nothing to do with the previous one, so your experience is there, but you have almost to start from the scratch, to start thinking in solutions, reading a lot, and we also have to keep in mind where we are. We are not a company that just have to give results, but we have to, let's say, teach students, we have to learn, we have to go beyond, and to do that, we have to start to think in, let's say, scratching and find problems and trying to solve those problems, or going beyond the merely engineering problem. And I think that's all. That's so bad.